Hello, everyone. Good afternoon, and thank you for joining us here. Okay, my name is Abhinav, and I'm a senior data scientist at Elsevier. And with me, we have Ram and Pranita, and we welcome you to our presentation. Today we are going to talk about how at Elsevier we work on improving scientific and clinical outcomes from a deep domain and generative AI's perspective. And OK, let's dive into it. Yeah. In today's agenda, we cover topics which focuses more on this aspect of scientific and clinical information and how we can provide it to our customers in a better form. We have divided our presentation in 3 parts, where I start with describing BC, which is about improving a large-scale model in a large-scale data pipeline. And then there will be Ram, who's going to talk about Scopus AI and how it harnesses generative AI, and he will share his knowledge and insights on the same. Then we'll have Pranita, who's going to talk about her experiments in some very interesting syntax and semantic of prompt engineering, and she'll share her insights in that. Okay, let's start then. Okay. So our biomedical content expansion program, it enriches 2 of our products, which is MBase and MBiology. Now, last year when we were here at Cypher 22, we talked in detail about our chemistry pipeline. We talked about how we improved this pipeline, and we had a lot more input of scientific research documents in our database, which supports this, which supports Reaccess. Now, Reaccess is a data searching platform where chemistry experts or researchers, they find substances, biological targets, and related information. And for their research purposes, it could be it can be industrial or just for scientific or educational purposes. Now, Reaccess itself, it leverages the image and text data, and it finds the most relevant entities in these documents, and which gets indexed and is provided in the Reaccess database, which is then used by our customers for searching from the terms and finding the most relevant documents according to their searches as well. Now, since we started working on this in 2020, we have seen a great increase in our input for patents. You see the results here, and they talk about themselves. Then we also actually got an award for the same last year. So leveraging this knowledge and this experience that we had with our chemistry pipeline, I wanted to talk more about our biology pipeline and how we use this information to improve our biology pipeline. Now, to give you a context, Elsevier started organizing scientific information in the late 1970s. That is when our MBase was first released digitally. Here, we started initially with manual annotation, manual process of extracting of data. Then, as time went on, we moved into manual plus augmented solutions, where we use these tools to extract information, make the process more efficient, more faster. With time, there were better technologies, and we moved on to automated pipelines with manual annotation. And our products like Reaccess, MBase, and Pharmapendium, all these tools, they use such processes to better serve our product. Now, MBase is a database for medical biology literature. It is one of the most popular tool of that kind, and is actually recommended by many regulatory authorities around the world. For example, Europe's EMA, FDA, and other regulatories like WHO. Now, going to in more detail about Embase, it covers all aspects of human medicine and everything related to biological science. Now, if you see this small example here on the right side, we have a term heart attack. When I search for heart attack, I see more than 500,000 results for the same. This is powered by our index database, which finds out all the documents or all the articles related to heart attack and also the synonyms, leveraging the taxonomies that Elsevier has collected and curated over the years. It's a big application. It is quite important for us because it sees an average of 6,000 entries every day, which constitutes to around 45 million records coming from 2,900 Embase journals and other journals that we cover. The main focus of this application or how it serves our customer is primarily focused towards systematic reviews or pharmacovigilance. It also serves for drug safety and compliances. Then we have another product, which is mBiology, and it focuses on our biological relationships and between the entities. So if you search for a protein, as in this example here, we see many relations between them. We see its relations with drugs. Then we have proteins which are related to it. And we also see effects on it. Is it a positive or negative effect? And it is all showcased with the Sankey flow here. We can also get articles which support this information. This is actually a very new product released earlier this year. And since we have started working on it, we have collected over 15 million relationships, which are supported by many journal full-text articles and abstracts, clinical trials, and such. Now, this was about our products. And now let's talk about what we are trying to solve here. Both of these applications are supported by a common principle of data pipeline, and they needed some additions to these pipelines, some improvements to these pipelines, and that is what we focused on. Here, in this case, we worked on relationships between entities. In the diagram here, you see in yellow, you see proteins. In white, you see diseases. In blue, you see these symptoms. And in this case, we see that protein A regulates sarcoma, which is a skin cancer cell, which is a giant tumor cell, and it is functionally associated to symptoms like cyst and pain. So we want to extract these kind of entities on a larger scale. From an NLP's perspective, on the top you see on the right side, we have an extracted sentence from an article which goes into our NER process, which is supported by our M-tree taxonomies. And we find these entities in these sentences. Then we pass it through our relation extractor model. And in this scenario, we see that MIR35 has a microRNA effect on MC. And once we have these relationships extracted, we put it into our knowledge graphs. Similarly, we support around 17 types of relationships and 17 types of entity. So this was our main problem that we were solving. Now, how are we solving it? Similar to last year, we have a pipeline which is connected to each other. Initially, we start with journal articles, which comes feeded in from our data lake. It goes into filters, which filters based on the legal requirements and the topics of these journals. Then different other kinds of filters based on their topics and also their sources. Then we go into NER, as I explained earlier. It is supported by M-tree taxonomies, and we extract entities. Once we have these entities, we pre-process them by attaching it to the sentences it was extracted from. We clean them. We add more information to that, which goes on to our next step, where we have these triplets from sentences, and we create subject-object pairs. With these subject-object pairs, masked in these sentences, we feed into our relation extraction model. Our relation extraction model, it is based on a BERT. And on the right side, if you see, we have specific models or specific relation models for each kind of relationship. And one might ask, why do we have so many models? The reason being the flexibility in this kind of pipeline. So we can add new relations, we can add, modify, or improve on these relations. Some of these relations are subtype of one another. So it gives us more control over that kind of relationships rather than a model getting confused because of its subtypes. Once we have this information that if two entities are related or not, we feed it into our effect extraction model. Now, our effect extraction model, it classifies the effect into a positive effect, a negative effect, or there is no effect at all, for example, in cases of synonyms. So once we have our relation extracted, the effect of these relations extracted, we put it into our post-enrichment process, where we add different other information like bibliographical information, sources of these information, anything that can help the end product to give us more reference into where this source or where this relation is coming from. With this pipeline, we have document-wise knowledge graph. For each document, we have knowledge graphs. We compile all these together. We put it into a bigger graph DB, which supports these applications, actually multiple applications. Now, this graph DB, it cannot be just kept like that and should be curated from domain experts. They work on these relationships. They actually see these documents, and they curate over it. So this is the whole pipeline, but now this pipeline is, we have a solution for this pipeline. How do we make it scalable? As I mentioned earlier, we leverage some knowledge from our experience in the past and from our chemistry pipeline. Now in biologic pipeline, we wanted to use same principles because it worked very well for us, where we created these data science Python components, which were wrapped in Java wrappers. The interface was our format conversion service, and we were using these kind of independent components as specific microservices. Now, these microservices, they are scalable because they can be vertically or horizontally scalable. Then we reuse these microservices as we used in both these pipelines also, actually. Some components were common, so we were able to reuse them. We can plug and play, we can change the order of these pipelines, and we can experiment with that. Then it is always easy to update them because they are so independent. And we also have this feature of accessing these components using APIs, where we can test specific components before actually deploying into the pipeline itself for better testing. Now, what was the impact? How did it turn out? So to give you more context, here we wanted to increase the recall of our pipeline because our precision was quite high, above 90%, and we wanted to work on the recall. And that was our primary focus. And we saw a great increase here. We saw more than 60% of recall increase, which was a big deal for the application itself. With this pipeline, we are able to process around 34 million abstracts, then full text, clinical trials, constituting to 15 million relationships coming from 1.4 million entities. Now, you might ask, how do we address this pipeline? How do we talk about this in a space where what we are talking, everybody is talking about large language models and the drug industry. Now, we see great potential in that, and my colleagues here are going to talk about how our experiment with those went. So LLMs are amazing. They work so well on text completion, text generation, summarization, dialogue creations. But for our use cases, specifically for a scientific tool or research tool, there are some shortcomings. For example, there are hallucinations. But as you know, as you can realize that in a research space. You want very accurate information. You cannot deviate from the accurate information. You cannot provide something else that the model thinks is right. It has to be very accurate. So we are working more towards that, how we can improve that. Then obviously it comes with large overhead of training data. Then how there are big computing resources that goes into training these models. Also, as Elsevier and having its own, own journals, its own data, IP is also a very big concern for us. So these are the factors, and I think in the further topics, you will see that where are we with these experiments and how, in which direction we are going. So I'll pass the mic to Ram here. Thank you.
Is it on? Yeah, it's working now. Thanks everyone for joining us in this presentation. Thanks Abhinav and the team for the intro. Let's get started with the next set of things that we are going to discuss today. Let's start with the problems and challenges that we face as researchers, in the early stages of their careers and academics. So mainly there are three problems. One is information overload. As data scientists, you are working on some complex problems on a daily basis, and you are looking for a lot of, research papers and stuff, and to keep track of things on a daily basis, and then, for references and stuff, it's a mammoth task. It has a lot of problem. That is information overload. And the second is, we are working with very cool technologies and stuff, which has a lot of data out there, like in forms of blogs and stuff. But then there are really niche research disciplines which doesn't have that, and that results in inefficient search, which doesn't have much information. And the third is there is almost or very less collaboration between disciplines across the world, the research community. So these three boil down into two main factors, that we are having very lower academic and societal impact, and we are also missing out a lot of potential opportunities. So these are the problems, and what if I say we have a solution, which is called Scopus AI. It is a search engine which is powered by the academic high-quality science content, which is peer-reviewed and has almost all the disciplines that are there in the world, in combination with generative AI. That's Scopus AI for you. So what does it deliver? So it has 4 main entities. So it has a capability of handling natural language queries from the users, and then it has a brilliant summary backed with references from research papers. And then there is deeper query exploration, which gives you a lot of queries which you use to learn more about the topic of interest. And the next is the visual representation, which we call the concept map of related topics and disciplines. I'll talk more about all of these. So this is the summary. So you can, as a user, you can have a search, a query, and then you get all of a semantically similar and relatable papers, which are significant, will be summarized. Along with that, you'll see the embeddings of the papers, as you see over here. And you can click on it, and you can see the reference paper in it. So that is the coolest feature, I would say. And this second and third are the go deeper and concept map. So as I said, you have a very limited knowledge on a topic, and you just go into the system, search for it. It will give you a summary of the related topics, but then it will also give you a list of questions, which if you follow up and read, will give a deeper understanding of that topic and also related topics. And then this will go on, so on and so forth, until you reach to a level where you have a broader understanding of that topic. And the second is concept map. I mean, visualization is always better than having questions in all the summary. So you'll have concept maps which will be having visual representation of the topic that you search for and the related disciplines. And this is the user interface of the Alpha Scopus AI. So as I said, you have that search query window and then the summary along with the concept maps. So this is how it looks, the Alpha product. But then we are actively working on the beta product. I mean, as we talk, I think it's all going to be live. And the next question is, how does it work? So we have a 6-step approach in which we will explain how it works. And all these 6 approaches that we are, based on the responsible AI principles that we have. And I'll move on to the next slide about, yeah. So this is about the content that we are using to generate all this summary, right? So we have, the curated academic content that is trusted by a lot, all the research community that we have because it is peer review, and we have a lot of content with us. And then the second is, it has been updated on a daily basis. So we talk about a scale of millions of papers that has been published across discipline to our system every year. And the next is the abstracts. That's the main, aspect in which we do the summaries. So, the query, it can be a simple keyword that you want to know more about. It could be a complex, summary that you already have that you want to know more about, or a title or a part of an abstract. So it can be anything, and it will be able to bring in semantically related and relevant papers based on that. And the next is, so what happens once you have a query in? So it will be transformed into a vector, obviously, and using our advanced language model, and then it will bring in the top 10 relevant papers based on semantical representation, and then it will be ranked using our proprietary, semantic relevance algorithm. Actually, there are a lot of aspects. One of it is cosine similarity, and then you have other factors like the recency of the publication, and then we have citation metadata, and these are the things that we use to create the ranking for the top 10 papers. So once you have that summary, it will be, once you have the top 10 abstracts, it will be sent to the LLM, and it is given custom generated, custom engineered prompts, which has been, in experiments with different versions, and then we arrived at something, and that will give you the summary that I was talking about. And there are many aspects that we, using which we generate the summary or the prompt using that. It is, one main factor is, it shouldn't fabricate any information. So, we claim that it is scientifically valid and factful, and the models, as you know, the LLMs, it can easily hallucinate with different responses that it could generate on its own. So that is one aspect we are trying to restrict the LLM with, and that's how we devised our prompts. Okay. So followed is a comparison between the existing Scopus application using the keyword search, and also it has a lot of other way to look for the papers that you have. You can use a lot of metadata, you can use a title itself. But then if you start searching for documents with just the keyword like you are going to do in Scopus AI, I mean, you'll get content that are not really semantically similar. Of course, it's not going to be. But then you'll have other metrics that's lexical, which is not that great when compared to the Scopus AI. When I'll show you the next slide in which you see the data. So for example, this is something to know more about the development of autonomous vehicles, and you see the summary along with the 3 papers with the relevance, as I said, using like how latest the paper is. You could see it picks up the latest papers from 2022, 2023, and 2021. But then there is one limitation here, that we are not using the citation metadata that we have to its full potential. The reason, I'll explain that later. So this is, these are the data specification and scale that we have used to generate this alpha product. First is, we are restricted to use, last 5 years of data, so which is somewhere close to 25 million abstracts. And then, 25 million articles. And I was talking about the scale of the scientific content that we have. So the last 10 years, it goes up to 45 million scientific papers. And the second is, I'll go to the third first. So the corpus spans from 2018 to 23, which is having all the latest publications. And the second is, we are validating the results of the LLM with 2 main criteria. One is the relevance and the coherence of the summary. So these are 2 main aspects we are considering. And about the citation metadata that I was talking about, so we couldn't leverage it because we are not using data from the past. So we are just using data in the last 5 years. So we are missing out on the citation metadata. And about the rollout, the Scopus Alpha is rolled out to 5% of the entire Scopus user base that we have. And I'll talk more about the prompt engineering and the 4 aspects that we concentrate on. As I said, our top priority is no fabrication, because it has to be backed by the scientific facts and things that are in the abstract that we give in. And second is, as I said, you'll be having inline citations for all the summaries. So that is also something we achieved through the prompt to LLM. And the third is to maintain objectivity. So, when you have, or when you speak about a scientific paper, you have a lot of metadata associated, like author details and so on and so forth. So, but then we are using abstract, and so we want to restrict the LLM to just use them to maintain objectivity, as I said. And the fourth is evidence-based, and this is due to, so this is achieved due to the 2 things that we use for evaluation, the coherent and the concise summary. So about challenges, we face the classic token issue when it falls out of the limit that we can provide it to an LLM. So it has, like, for example, you give a topic and then you get 10 huge abstracts, and then you'll not be able to pass everything into an LLM. So that's when, we are just truncating the results so that it could fit, like the top 5 results or some n number, so that it could fit into the, we can pass it to the LLM and there will be smooth processing. But of course, we are working on some more context-based sophisticated solution to encounter this better. And so I just want to make a quick note of the Scopus AI demo that we are going to have in the keynote page tomorrow. Please attend that as well. You can see it in action. And okay, about what we have in our roadmap in the near future. The first is, right now we are dealing only with abstracts and stuff. We are not dealing with any profile or author-related stuff. So, as a Scopus user, you could be working on one or two multiple domains or disciplines. So what if we have the search history of yours and we could give you more personalized solutions using LLM? So that is one area we are going to work upon. And the second is people finder, using which if you know an influential author and you want to follow the work of his, so you can just get more updates of the work from his or her. And the next is, so now the corpus is restricted to 5 years, as I said. So we are going to incrementally increase that from 25 to 45 million. That's a 10-year data span. And the next is, incrementally rolling out to all Scopus users eventually. And the last is about the feedbacks and improvements. So we are actively, looking for feedbacks from people. So if you see the, user interface, you could see, there is a feedback loop, available for every aspect that we are giving out for the user, be it summary or the visualizations. We get active feedback from the users and the research community for whom we have rolled out it for now. And we are constantly making efforts to make this product better. So that's it from my end. Thank you. I'll pass on to Pranita for her.
We all three will present, and then later we'll take questions together. Is that okay? Thank you. Yeah, so my colleague, they have presented how we are migrating our product, how we are transferring our product from large language models to large language models. We have, team, me, Samir, Priyanka, our SME, we performed a small experiment wherein we wanted to see how the prompt, the syntax and semantics which we are using to design these prompts will affect the response of the model. So basically, we can say that we were checking the efficacy of the model with the help of how you are writing the prompts. So nowadays, there are pre-trained models available, and we wanted to check which model will work better for our domain. So here, as Abhinav and Ram both have presented that we are working in domain which is medical, scientific, clinical domain, wherein we do not want our models to hallucinate. We do not want users to have responses which are inferenced by model. We do have our data already in our databases, and we want it to be extracted but not inferred by the model. So for that purpose, this is a small experiment with the motivation of asking few questions. So we had few questions for this experimentation, that what are the different ways with which we can develop prompt templates. So there are different templates we are working with LLM, most of us. So we know that there are different templates which we use to query a large language model. So what can be the different template? Which template will basically work for me? Now we have many tasks which we perform based on our application. So for a particular task, there can be different models. So the main question is, can I use a single model which will generalize well for all the tasks? Or if my application demand only one task, then can I only concentrate on one model which will work better for that task? So for that purpose, again, that was also one more motivation for this experimentation. Then matrix, of course, only from the prompt will I be able to know that this prompt will work better or not. So few metrics I'll display here in the following slides as well. And we also observed, very interesting observation was there, that when we were making minor changes in the prompt, when we were writing the prompts, those minor changes were getting reflected in the response of the model. So I'll take you through that. We concentrated on these few tasks: open book QA, closed book QA, summarization, dialogue, paraphrasing, and named entity recognition. So let me tell you something about the task. When we are talking about open book QA, there are three things which we add in the prompt. One is context. We have a paragraph, we have a text. There are instructions along with that paragraph, and then we have a query. So the query is nothing but a question which we are asking to the model. And specifically in open book QA, we want the question to be answered only from the paragraph. We do not want model to infer something out of that paragraph which is being given as an input. In the closed book QA, we want model to extract the information from the data which is being used to train that particular model. So the aspects or the intentions are different here in both the question answers. Summarization, task, Ram has very well explained it. Dialogue, so it's like having a dialogue, how we have a dialogue with ChatGPT kind of thing, wherein we expect model to answer more naturally. So it should appear like a dialogue and not question answer. Question answers can be more scientific. Dialogue need to appear more natural communication. Paraphrasing, so in our case, in our domain, when I'm talking about scientific and medical domain, paraphrasing is little, we look at it from different aspects. We say that here is a text and I want to paraphrase this text or simplify this text in such a way that a junior clinician will understand this. Or here is a text, this is a medical text or a scientific text and I want this text to be simplified in such a way that even a 5th standard student will be able to understand it. So that was our intention for paraphrasing. And named entity recognition, so we wanted to identify medical, scientific entities from the input text. So the prompts which we were using, we were designed for these different tasks. The data which we used to experiment was from open source books, papers, and some of the data, some of the prompts, some of the paragraphs were manually generated by our subject matter experts. When we are talking about prompt, so basically here I'm highlighting syntax and semantics. So syntax means prompt components are, we have instruction, query, context in general. So how I'm ordering these 3 components, whether I'm writing instruction before, where I'm writing instruction after, that also we saw the changes in the response of the model even with that syntax. So semantics is like whether I'm giving an example to the model when I'm querying, like one shot, that okay, this is a text and this is a paraphrased version of the text and I want you to give me a paraphrased version in the similar way for another new text. So this is a one-shot learning. Zero shot is wherein we are just giving a question and we want model to understand that question with the help of the instructions and model will generate the answer. Chain of thought wherein we are simplifying, we are breaking down the complex problem and then we are trying to give those instructions to the model and then we are trying to see what can be the output. Third one is more interesting and more specific to our domain because our products are used by clinicians, patients, students. So whenever there is a response from the model, we want that response to be user-specific. Like, so suppose if I'm saying that there is a same question which is asked by a junior clinician, same question will be asked by a patient and let's say some student, but the answer should be different. I'm not saying that the fact will differ, but the way in which that answer is presented or responded by the model need to be different. So we experimented a lot with this role and persona as well for this experiment. So these are the models which we used for our study. We used GPT 3.5, Llama 7.13, Vicuna 7.13, and Falcon, the small model. We used different prompts, 50 examples almost, 0 shot, 1 shot, without persona, which I was just discussing, with and without instructions. So I'll tell you what is with and without instruction as well. Sometimes you just fire a question and you want model to understand from the question and answer, and sometimes you just give detailed instruction to the model that do this in this way, and we want model to understand that instruction and follow. So that is actually with and without instruction. And in the evaluation, now we all have been repeating it that we are in a medical and scientific domain. So for evaluation, just the quantitative metrics are not enough for us. We wanted qualitative metrics as well. It is not just a representation of the fact by the model, but we want to see how these facts are also presented to the user. As I said, there are different personas of our users. So these qualitative metrics were also equally important to us. I'll talk about the quantitative metrics which we have used. So specific to summarization, we have used Blue, Meteor, and Rouge score. We didn't use a single metric here because we already know that these are biased. Like Blue works with Ngram, Rouge works with Unigram, longest subsequence, Rush L. And Meteor is the more semantics. It also work with synonym and stemmings and try to find out the overlap between the actual and the predicted summaries. So we have taken all of them, and just to see we are not biased towards any of the metric. So when this is the result of our experiment. Here I'm showing it specifically for the summarization task. So here we can outright see that GPT 3.5 outperformed in all the metrics. We can see it here. We wanted to see the rationale behind it, that fine, we are using it as is, we are not fine-tuning these models. So still why the performance difference can be there. So we can put it on a, in a simple words, we can say that these score, this is the same table, just textual representation of the table, that GPT 3.5 stands out here. Now that was for summarization. For the general task, if we are saying, these smaller models' performance observed to be good with dialogue and multi-tone. What can be the reason behind it? So as I'm saying that these models basically were trained to have a chat with the user. And when we are firing the questions, let's say we are dealing with the tasks such as dialogue or multi-turn question answers. So this is kind of chat with the model. And that's why we found, or we observed that the smaller models were working good with the dialogue and multi-turn. However, when there was a task which was having implicit information extraction, following the instructions properly, responding with the help of the tone persona, these models couldn't do well. They couldn't understand. They were just, sometimes either they were hallucinating, sometimes they were just responding, or sometimes there were funny responses, which I'll share with you at last. Llama 2 specifically for open book QA inferred knowledge and it over-explained, whereas we don't want that. In our domain, we are saying that whatever is there in the paragraph, you give it as is, specifically for open book QA. If it would have been a closed book QA, we want model to infer something and add something of its own, but not for open book QA. In that case, GPT 3.5 worked better than that of Llama 2. And surprisingly, none of the models worked good for paraphrasing and NER. Again, reason being, because our domain is medical and scientific, and these models are trained on a general data, and that's why they were not working good probably on NER and paraphrasing. So as I said, that qualitative and quantitative metrics. So here, why I'm highlighting this, that the best prompt, zero shot with persona and precise instruction. This is our general assumption that whenever one-shot prompts are being used, the performance is good. And still I'm highlighting here that zero shot also was working comparatively on the similar way. Now, as Ram has already mentioned, that there is a restriction of the token limit whenever we are dealing with the models. And if you are using one-shot prompts, then already you are consuming a lot of tokens. And then probably a model will not perform well because you're consuming tokens, and it will have limitation. It will just clip down most of the data when it is, most of the query content when it is actually firing the query to the LLM. So if your task is something like this, wherein you are more interested in just using the pre-trained model over there and you want to check how it will work, then our experiment, I'm talking only based on our experiment. So from that, we observed that zero-shot prompts were also giving almost similar output as compared to one-shot prompts. GPT 3.5 responded well with the change in the tone. So when we said that this is what is Alzheimer, let's say, and explain it in such a way that even a 5th standard student will understand it. What is Alzheimer? Explain it to a junior clinician. So for both the queries, GPT 3.5 was giving the fact by changing the tone so that it will be understood to the user persona or tone. Again, the same thing for tasks like NER, paraphrasing, the performance of the model was poor. And we saw GPT 3.5 and Llama as comparatively were the better model as compared to the other. Quantitative, we have already seen that GPT 3.5 again outperformed. What is the rationale behind this. Okay, so before that, I'll take you through the example, sorry. So this is an example I just wanted to show you instead of just visualizing what would have happened. So this is one example wherein, look at the general instruction which is given. So this is a system message. We give, there are two ways with which you can instruct a role or persona or to the model. One is you can put those detailed instructions in the instruction itself, or you can put it in the system message of the model. So in the system message, we had put that you are an AI model which can follow input instructions. The model is a text summarizer. I'm taking an example of a text summarizer, that's why. And it is capable of constructing summaries of a medical and scientific text. And the instruction which was given in the prompt is generate a summary of below text, and then the paragraph was given. On the other hand, the second prompt, system message is same, there is no change in the system message, but if you check instruction, generate a summary of this large text by dividing the text into chunks, then and summarize the chunk, then merge all the summaries and summarize it again. So this is quite detailed instruction which is being given to the model, and show the intermediate summaries too. So here you can see the big difference between the syntax and semantics. So you can say this is the big difference. There is a detailed instruction, and this is quite abstract instruction. And we will see how the results differ. So for GPT 3.5, when the general instructions were given, we saw that it generated the summary. There was a large text, and it just gave the summary. But when the detailed instructions were given, you can see that there is one paragraph, second paragraph, third paragraph. So paragraph-wise summaries it has generated. It didn't mention that amongst these paragraph-wise summaries, where is the merged summary and where is the section-wise summary. Unlike to GPT 3.5, in Llama we saw that. So you can see this is a general instruction, and it gave a one paragraph summary of that three paragraphs. And here, when the detailed instructions were given, you can see it here that it gave us a summary, and then it also gave the title, section summaries. So this is a summary of the merged summaries, and this is a summary of the sections altogether. And this is 13 billion. And now, if you go to 7 billion for the general instruction, as the text was too large for the model to handle, so it simply didn't respond. There was no response. What can I do for you? What can I do for you? It was just giving us that response. And for the detailed information, at least it could give us some summarization. So here you can see that even if the model was smaller, if the instructions are given in detail and properly, then even a smaller model can give you some result. It's not a wrong summary. Our SME have validated the summaries. So this is a right summary. But when a generic instruction was given, it couldn't understand it at all. And when a detailed instruction was given, we can see that there is a summary. And for Vicuna, 13 billion and 7 billion, the detailed instructions were also not working well. They were just paragraph summaries were given. For Falcon, we didn't get the response because the text was too large to be handled by the model. So this is an example just to show you how it worked well. The big question was that why these models are working like this, why the responses are like this. So we wanted to see the rationale behind it. So we went through the data cards of these models, and we saw that GPT 3.5, it is being trained on a huge corpus of Common Crawl, English Wikipedia, and expanded web text. And that's why it was understanding not only the generic domain data, but also the scientific and medical one. For Llama 2, it was specifically optimized for dialogue use cases, and that's why it was not working good for open book QA kind of task, because therein it is being specifically trained to extract the information from the database and give it in a natural way. The Falcon 7 billion model, it's an instruct model. The 65% of the data which is used to train this model is from this base open source chat model. And there are 100K dialogues generated by letting ChatGPT chat with itself. And that's why we saw that it couldn't generate summary at all. A Vicuna model is fine-tuned on Llama, and it is trained on 52 human conversations. in their paper, they have a disclaimer that our results can be biased towards the data which is being uploaded by users on the internet. So probably that can be the rationale. This is what we have inferred from our experiment. And we wanted to see that how these prompts, because we are now looking towards improving our products by leveraging large language models. So we wanted to see whether it is only selection of the model is a question, or it is also writing good prompts, or how well we can write the prompt, which prompt is a good prompt, which prompt is a bad prompt. Do we also need to work on a system meshes side when it comes to applications? So that's why that was the motivation or objective of the study, and we found these few of the findings here. As I said that the models were specifically trained to have a chat with the user. So sometimes we also saw when the model couldn't understand the instruction, there were funny responses from the model. So you can see here, I have completed assigned task. So whatever may be the task, it was just saying I have completed assigned task. There was no response. Then I have completely understood your instruction, whereas it was not following the instructions at all. It was just saying I was completely understood. Thank you for detailed instruction. Cherry on the ice cream. This message will be processed within 15 minutes. Please do not contact me until then. So these were the funny responses we saw. I'm processing your data. Do not message me for next 15 minutes. So now, again, it is logical. It is not illogical, because these models are trained to have a natural language conversation with the user. And isn't it a natural language conversation? It's a natural conversation, right? So whenever models are not understanding the complex instruction, they are coming up with these funny responses, we can say. So to summarize, as Abhinav has already mentioned about it, that in our, in Elsevier, we are dealing with medical and scientific domain. So to summarize, we can say that even if these models are there, we need to work on these few limitations and few aspects, that it needs a lot of data, a lot of computing resources, some complex reasoning. We cannot afford hallucination in the models. Our domain is very sensitive to hallucination. So to summarize our talk, I can say that we talked about improving a large-scale research data pipeline, which Abhinav shed a light on. Scopus AI, we are leveraging large language model to improve our traditional Scopus AI product, Scopus search product, wherein it is giving you more and more better recommendation for the papers by selecting topmost papers which are more semantically relevant to the user query. It is also doing some query augmentation. And then the experimentation is selection of the model is task specific. Sometimes you want a model to do everything, and sometimes your application says that, no, I am interested only in summarization. Then why to go for that model which is doing everything but not doing good, probably not doing that good in summarization. So we can concentrate on this aspect, that what task I want to use this LLM for, and then probably I'll experiment with few, and then I can fine tune it on my data. Of course, we saw that performance of the model differ with the prompt style. And the key to get good response is write concise prompt, considering system messages, structure, and style. So this is all from our side. If there are questions, you had some questions. Yeah, you can go ahead. Thank you so much. Yeah, please.
Yeah, Pranita, thank you so much. Talking about large language models, and you have silently implemented, and you did a comparison also, not only GPT 3.5 and compared with all other open sources. It is really, I think, a very useful information for the people.
Thank you.
I think for prompt, I think you touched in the prompt engineering other things. Also, when Ram covered, when we search for a particular paper, it gives you some options, reference, ranking 1, 2, 3, and all. So we did purely rely on the prompt engineering and zero-shot, one-shot, or we have a combination of GPT models and then traditional NLP model, so that we can get, because this is in a productionized. It's just not like, backend you just connect the APIs, and that is the first question, saying that, how did you manage to do that? Second question is like, how did you, little bit of on a data engineering side, because you will be having the huge text on the earth maybe, because any other enterprises, if you compare the knowledge bases, articles, I think elsewhere we'll have so much of articles in that. How did you manage the data engineering part, and then how are we able to continuously the inflow of text, and then how we manage that, because you're covering up to some 5% or something for the users. So maybe a little bit of it if it is shareable, because this is a very good one.
Yeah, I was about to say that as well. Ram probably will be able to share whatever we can. So the first question was related to whether it was solely prompts or there was something else than that of the prompt. So Ram has already covered one slide wherein specific prompts were written, of course. At the same time, for the ranking specifically, we also used metadata. So that metadata was also used to have rank of those searched papers. Combination of it. And LLM is used for summarization. And there are other models which are also used, and there is some engineering which is done, data engineering which is done, other than the LLM as well. Ram, please, would you like to add something?
I think she has answered the question, but then I'll just touch upon a few things. So we have a language model. I mean, you were asking about the ranking of papers, right? So that is not a work of prompt engineering. It is based on two things. One is the vector search, the results of on which it is ranked. Along with that, we have a few algorithms based on the citation metadata and few other things that we will not be able to share about. So, but then these are the two main things.
Yeah.
So yeah, that's it.
Yeah. So the papers were indexed. So we have a vector database, and then from there, some data engineering steps.
I don't have a proper answer for that, but I think this we can take it offline. If you want to know further about the pipelines and stuff, we can talk.
Yeah, please.
Hello. So I have been recently working on similar medical information and clinical trial notes. So one of the challenge that I faced is the embeddings and retrieval. For example, if the user is asking systematic lupus erythematosus, it's a special medical condition where other business user would go by word SLE. So for normal English textual data, this might work. For example, running versus run or walking. So all these embeddings are slightly closer, and then the retrieval also will be good. But what specific technique used are the models that were helpful for writing the retrieval mechanism better? Because that's being the key part. If you are getting the data and then it's going to the LLM, right? So how did you handle this business specific or domain specific answering?
So you are asking for Scopus AI?
Yes,
or the model which...
In general, where the part where you embed the documents and later on you retrieve the documents, right, based on the user query. So imagine the user query could be two different terms and it could be very specific medical term. So how does this embeddings work? For example, if you go by BERT, uncased, it can work for normal English text, but it was not working for this medical specific things.
Yeah, that's a good question. You want to go?
Yeah, I have another question for you as well. So the thing is, what model that you are using and what is the content that it has been trained on. So, our model has access to these medical and scientific content, which will talk more about the keywords that you talk about. So it has a better chance of giving back a result that is semantically relevant than a generic model, which is out there.
So when you mention your model, is it something specific you used for embedding? For example, let's assume I'm using a open sourced one like flag embeddings, which is slightly in higher position in the MTB ratings. So is that something that you have inbuilt in your organization based on the all medical data?
I got it, but I cannot reveal much. But what I'll say is we have experimented with a few open source models as well. But then we have few that we fine tune for for our use case in specific. So
thank you.
That's all I can say.
Sure.
I think one last question and then we'll,
I have two questions. One, you had mentioned that there are differences in the model performance. This can also be because of attention within the data set, because every citation might have very similar words which the model is actually learning. And the metrics which you have used are quite balanced both on precision and recall. So can it be that the model is just understanding the perspective of keywords which it needs to attend on, or it is really learning? Has that been tested?
No, actually, that's really a good observation. Here, we wanted to see the efficacy of the prompt on the model response. because we did not fine-tune any of the model. We just used the models as is. And we wanted to see that just writing, because we observe this, that when I'm writing a prompt in a certain way, it is changing its response. Sometimes it is giving proper response. And then we wanted to have a detailed study.